Alright, so let's begin this lecture on kinetic theory of gases by giving a kinematic interpretation of two key state variables in thermodynamics, which is pressure and temperature. Like we said in the introduction, in case you didn't watch that, the system we have in mind is an ideal gas in thermal equilibrium, okay? But the way we have to model it in kinetic theory is, okay, it's a container, a box like this with rigid walls, and it's filled with a large number of particles, all of them identical because we think of single component systems of certain mass m, and these particles are just bouncing around and colliding at times with the walls of this container, right? And having very complicated dynamics. So we say, like I'm saying, that the system is in equilibrium, and this has consequences in the density of particles, but also in the distribution of velocities, as we are going to see in this first video. Actually, we are going to break down this first part, which is interpretation of pressure and temperature, into two videos, because it's going to be too long otherwise. So, fine. This is the issue, right? So I'm telling you that these particles are colliding elastically with the walls of the container, and these collisions transfer some momentum to the walls, and it is this force that is exerted on every infinitesimal surface element of the walls of the container, which is going to create this notion of pressure. That's the intuitive notion of pressure, and we are going to try to see if we can learn something about the pressure as in thermodynamics from the kinematics of the system. So fine, to do that, let's analyze what happens in one collision, right? So I'm going to zoom into this region here, and what you have there is the floor, well, I mean the floor, the lower wall of this container, yes, making it like this, and the particle is coming, and then it's going away. Okay, so it's a particle of mass m. Let's say that the velocity, the modulus of the velocity is v, of the incident particle, and okay, this is a point of collision. This bit here that I'm going to highlight a bit darker is this surface element d sigma, and the particle is going to come with an incident momentum p, then it's going to collide and it's going to go away, and the outgoing momentum is p prime. Because we say that the collision is elastic, of course the modulus of p equals the modulus of p prime, which is nothing but mv, right? Because that's what we are given here. And then, well, I just want to write what is the momentum transferred to this surface d sigma in one collision. So I'm going to draw the normal to the surface of the container, of the wall of the container, and this angle here I'm going to give it a name, theta. Of course this other angle here is also theta, and if you like as well, this angle here is also theta. I'm going to use that later. Yeah, so I just ask myself, what's the change in momentum from the point of view of the particle? And this is p prime, no? Minus p, final minus initial. And I want to project that onto the relevant direction here, which is the vertical, the normal to the surface. So the unit vector, which is normal to the surface, I'm going to call it n. So I just multiply by n, so I'm in dot product with n. And that's a change of momentum in the relevant direction from the point of view of the particle. But I care about the wall, not the particle. So from the point of view of the wall, that's going to be minus that. That is the momentum gain of the wall in a single collision with a single molecule. Okay, so just looking at the picture here, because we know that this angle here is theta, and the other outgoing angle is also theta, and that the momentum is the same for both incident and outgoing, the particle in the incident stage and in the outgoing stage. What we have here is minus twice of m v cosine of theta. That's what you get when you do the difference of these vectors and you project it into the vertical direction. Now we can compress notation a little bit here if we define a system, a reference system like this. This is the z-axis, and if you like, okay, this is the y-axis and the x-axis, but we are not going to care too much about these two. I'm just saying that the z direction is positive, going up, away from the wall, And what you can see here then is that the incident velocity, okay, which has components x, y, and z. Well, the z component, as you can see here in the drawing, is minus v cosine of theta. Okay, that's the z component. Why it's minus? Because it's going down, and the positive z direction is going up in my choice of coordinates here. So you have the minus here, you have the v, you have the cosine, so what you can write instead is 2mvz. That is the momentum transferred by an individual collision to the wall. Okay, so I told you before, well, I'm not sure if I told you before, but the pressure is going to be the momentum transferred during time interval dt by, in principle, more than one particle which are going to be colliding with the wall. So we have to ask ourselves, if I have a time dt, I want to know what's the force that the particles are making on this infinitesimal surface element of the wall of the container. So to do that, let me maybe repeat this drawing. I will just copy paste, okay, because it's faster. Just give me a sec. Put it there. Okay, so I'm going to delete a bunch of things. I'm going to delete everything. I just want the line. Fine. That's the z direction. So what is the total number of particles that is going to impinge in this differential element of area here? Well, it's all the particles that are contained. I'm asking myself, so let's be precise, I'm asking myself how many particles are going to collide with this infinitesimal element of area in a time dt, so the time that is passing is dt, with a velocity in the infinitesimal neighborhood of b, where b is certain velocity specified with x, y, and z component. So I'm looking to all particles which are parallel to each other, exactly parallel, which have enough time to approach and actually collide with the infinitesimal element of area, d sigma. So these particles are all going to be contained in a cylinder which is slanted because with the axis parallel to the velocity vector, and the height of the cylinder is going to be vz dt. Okay, so because this is the particles that actually have time to collide with the wall in the time interval dt. Okay, I switch on the clock and then I wait dt and I switch it off. I want to count how many particles with that specific velocity hit the wall. So, of course, well, let's go by parts. So to begin with, I need to know how many particles are there per unit volume, okay, in this system. And because the system, I said before, is in thermal equilibrium, one thing I know for sure is that it's homogeneous, so the density of particles is the same everywhere, and it shouldn't depend on time either, okay? So implicitly, if you want to be more subtle, you are assuming that there's no external fields applied to the system, because the system could be in a stationary state, but it could have a gradient of density, and this is something that actually happens when you have, for instance, a gravitational potential, and your system is large and massive enough so that you can actually see the effect of gravity. Or if there are some external fields, magnetic, electric fields, or whatever. We are going to assume this is not the case. So the density in our system, either because it's small or because really there's nothing else perturbing it, it's uniform, okay? So this is actually a constant of my problem, and I can use it. So I know that per unit volume there are np particles. But I know that this little volume that I have here, this cylinder, has volume d sigma, which is the base, times vz dt. Okay, so now this product counts all the particles that are enclosed at any given time in this cylinder of this size. Okay, now these particles are of different kinds. So these particles are not all coming with this velocity. Some of them are actually going away. Some of them may have like larger velocity. Some of them may have lower velocity, and they may be moving in completely different directions. Okay, so I just want to count how many particles have that velocity. Okay, so for this I have to introduce a new little bit of notation. and I'm going to write the probability of finding anywhere in the system a particle coming in the velocity or in the infinitesimal neighborhood of velocity v, that is between, sorry, this is red, so between v and v plus dv. I'm going to call that some probability distribution that depends on vx, vy, and vz times the infinitesimal volume element, if you like, in velocity space. So dvx, dvy, and dvz. Okay, so this gives me the probability of finding a particle which is moving with this specific velocity. Okay, so if I have all the particles in the cylinder and now I multiply by such probability, I have counted all those particles which are at least infinitesimally close to being parallel with the velocity that I care about. So all the black highlighted particles here. Okay, so let's do it. I will just make more compact notation because I don't want to write all of this. I write this calligraphic p of the vector v, and here I have d, let's write it like this, d cube v. Okay, and of course I care about the momentum that each one of these particles is transferring to the wall. And this is what we calculated before, 2mvz. Okay, and I can take this whole thing, right, if you want, and I can divide by the time in which this process happens. So this whole object here is the total amount of momentum that is transferred to the wall in an infinitesimal time interval dt. Okay, so that's it. And what this is nothing but an infinitesimal force that is exerted on the wall. Okay, df. So as you can imagine, this df divided by d sigma is going to give me the pressure when I integrate over all possible velocities. But this is something we have to do first. So because we have introduced this new object, no? So this probability distribution of velocities, we have to explain it a little bit better, and that's what I'm going to do in the next video.